All right, and welcome to week 7 lecture. And we're doing this a little bit differently today. Rather than just looking at the computer screen, I've actually printed these things out, and we're going to kind of divide the lecture up into 3 primary parts. We're first going to talk about series circuits, then we're going to talk about parallel circuits, and then we're going to put them all together with series and parallel. Now, when it comes to circuit analysis, there is one primary law that you will use over and over again. Remember, in electronics, when in doubt, Ohm's law. Remember Ohm's law. When we have voltage equals current times resistance, or if we know the voltage and the resistance, we can find the current, or if we know both the voltage and the current, we can find the resistance. Now, you may remember that I said many moons ago that there were 4 laws that dealt with all of electronics, and I'm just going to go ahead and write that right down here. They were called Maxwell's equations. And the first of those is, of course, Ohm's law, number 1. Now, when it comes to series circuits, we first start talking about number 2. And number 2 is Kirchhoff's current law. Well, that would actually be number 3. So let's go ahead and do number 2, which is Kirchhoff's voltage law. And Kirchhoff's voltage law basically says that the sum of the voltage drops around any closed loop, and that's the key word here, closed loop, will always sum up to 0. So if we take a quick look at our actual circuit right here, remember this is the plus, and when the voltage goes through and around, note that the resistors are series opposing to the source. So we have a plus towards a plus and a minus towards a minus. So if we add these up and we start at this point here, if I go around this closed loop, that means the voltage across resistor 1, note this is in series aiding because we see the plus sign first, the voltage across resistor 2, and the voltage across resistor 3 minus the voltage of the source, because see, we see the negative sign first, that sums up to 0. Well, that's kind of good to know. So that if we have a circuit like this one here, where we have a 9-volt voltage source, we've found that we've measured 5 volts across resistor 1 and 750 millivolts, or also known as 0.75 volts, across resistor 2, we can simply find the voltage across resistor 3. And the voltage across resistor 3 will simply be 5 plus 750 milliwatts, which is 5.75 milliwatts, or I'm sorry, 5.75 volts, and we subtract that from 9 volts, and that means the voltage across resistor 3 is 3.25 volts. See? Nice thing to know. So Kirchhoff's voltage law, number 2, the sum of the voltage drops in a series circuit. Now, this is the biggest trouble that most people have in determining what is a series circuit. How do we know things are in series? Well, we know things are in series because they actually have the same current, not the same value of the current, but the actual same current flowing through all of them. So if two things do not have the actual same current going through them, then they are not in series. Note that when things are in series, these are known as voltage dividing circuits. Why do they divide the voltage? Because these all have to add up to the source. So series circuits share the current, divide the voltage. So our next topic is, how do we deal with a bunch of resistors in series? Well, how many of you have done the complicated math such as addition? Yes, it is just that simple. We find the total resistance seen by a voltage source by adding up all of the resistors values in series. Now that's pretty easy when you have several resistors of the same value. If you have, for instance, 4 resistors of the same value and they all happen to be 1K, you would simply find the total resistance by taking 4 times 1K, which would give you 4K ohms. Now, if I had 5 resistors, 1K, a 3.3K, a 1.2K, a 500, and a 10K, and these are in series with each other, note that we add them up and we find it to be 16K ohms. Now if we have 4 resistors, all that were 1.2K ohms in series, what is the total resistance? 4 times 1.2 gives us 4.8K ohms. One thing to make sure that you are aware of when you are analyzing a series circuit is the fact that the resistance, the more resistors you add, the higher the resistance becomes. So more resistors, higher value of total resistance. And that's always a good gut check. One, if you had, for instance, the 1K, the 3.3, the 1.2, the 500, and the 10K, and you came up with a resistance less than 10K when they are in series, you know, since 10 is the largest one and it comes up less than that, that you probably made a snafu somewhere in your calculations. Now, how many of you remember the equation for power? That's right. Power is equal to the voltage times the current. And the total power that is dissipated in a series circuit is always equal to summing up or adding the individual power dissipated in all of the elements of the circuit. So when analyzing a circuit, this is also an excellent gut check to see if you got the right values, is to look at the power of each individual element. If they add up to your calculations for the total power, which is the source voltage times the total current, then you did good. Now, we are now going to do some analysis of a series circuit. So, what are the general steps in analyzing a series circuit? Simply, 1, we know that the current has to be the same for all components in series. So if we find the total current, we know the current for all of them. And to find the total current, typically we need to first find the total resistance by adding up the values of the resistors, and then we use Ohm's law to find the total current. Now, then after finding the current that is the same for all resistors in a series circuit, we simply find the voltage across each and every individual resistor by once again applying, you guessed it, Ohm's law. And once you find those voltage drops, you can then find the power dissipated in each and all elements, add those up, and that should equal the power dissipated. So let's do our first circuit. Okay, and now we are going to analyze our first circuit. Now we can identify this as being a series circuit because we have how many paths for our current to flow? Well, it's only one. So that means the current going through resistor 1 must be the current going through resistor 2 and 3 and 4. So the first thing we typically do is find the total resistance. So resistance total is going to be equal to R1 plus R2 plus R3 plus R4, which is 3.3K ohms plus 1.2K ohms plus 600 ohms plus 900 ohms. And what does that indeed give us? Well, let's get the calculator out. Alrighty, so gotta turn it on. 3.3K plus 1.2K, and don't forget the K's when doing the calculation, plus 600 plus 900 equals 6, and 10 to the third means 6K ohms. And I'm going to go ahead and take this information right here and write it right down here because we have found it and we can put it right there in our table. Now, what law are we going to apply to find the total current? Let me guess. Oh, that's right. When in doubt, Ohm's law. So, when I do Ohm's law, I'm going to find the total current. That is going to be equal to the voltage source divided by the total resistance. And that is going to equal 12 volts divided by 6K ohms, which equals 2 milliamps. Oh, how exciting. So let's go ahead and write that down here. Now, remember we said this is a series circuit, and a series circuit all share the same current. And I love it. We don't have to do another calculation because this is a series circuit. I can go ahead and say, hey, I know the current in resistor 1, it's 2 milliamps. In resistor 2, it's 2 milliamps. Resistor 3, it's 2 milliamps. And resistor 4, it's 2 milliamps. Oh, awesome! I love getting things for no effort whatsoever. Now, we are going to calculate the voltage in R1, which we know is going to equal to Ohm's law, current times resistance, which in our case is 2 milliamps, times 3.3K ohms, which gives us 6.6 volts. If we take resistor number 2, so we have 2 milliamps times 1.2K ohms, and that gives us 2.4 volts. And then for our next one, we have 2 milliamps times resistor 3, which is 600 ohms, which gives us 1.2 volts. And last but not least, we have 2 milliamps times 900 ohms, and that equals 1.8 volts. Now, we need a little gut check here because we had said, and I'm just going to go ahead and write those values right up here. So we had calculated, this is 12, so we have 6.6 volts here. We have 2.4 volts here. We have 1.2 volts here. And we have 1.8 volts here. So let's go ahead and add these up. We have 6.6 plus 2.4 plus 1.2 plus 1.8. Well, let's go ahead and add those up. 6.6 plus 2.4 plus 1.2 plus 1.8. Indeed, oh, how about that? They equal 12 volts, exactly like they should. Now remember, I like to draw on my diagram here, what was the total current that we found? Well, we found the total current to be 2 milliamps. And remember, we have 2 milliamps going through resistor 4, 2 milliamps going through resistor 3, 2 milliamps going through resistor 2, and 2 milliamps going through resistor 1. Now, how do we find the total power? Well, that is going to be our voltage source of 12 volts times 2 milliamps, which gives us 24 milliwatts. And 2 milliamps times 6.6, here we go, 2 milliamps times 6.6 volts equals 13.2 milliwatts. And 2 milliamps times 2.4 volts gives us 4.8 milliwatts. And 2 milliamps times 1.2 volts gives us 2.4 milliwatts. And 2 milliamps times 1.8 volts gives us 3.6 milliwatts. Now let's go ahead and add those up. The 3.6 plus the 2.4 plus the 4.8 plus the 13.2, by golly, adds right up to the 24 milliwatts. So, yay! Everything worked out beautifully. So now let's go ahead and do another sample. Now, in the actual lecture notes, I have already provided the answers for that first one. But this next one here, we are going to do together. So you might want to write these down on your lecture notes printed out as we go ahead and analyze this. Now, is this a series circuit? Well, let's take a look. Is the current, same path, same path, same path. So the current is the same for all of them. So this is indeed a series circuit. Now, the first thing we want to do is add up and find the total resistance. So total resistance is going to equal R1 plus R2 plus R3, which is going to be 1K ohms plus 1K ohms plus 2K ohms, which equals 4K ohms. So we can go ahead and write that right down on our little table here. And then, of course, we're going to apply what law? Yes, that's right, Ohm's law, to find our total current. And our total current is going to be equal to our voltage source divided by our total resistance, which is equal to 5 volts divided by 4K ohms, which gives us 1.25 milliamps. Now remember, so I like to kind of write that down here. So I know my total current so far is going to be 1.25 milliamps. Now, note, because it's going to be going through resistor 3 here, we know that that's going to be 1.25 milliamps. And resistor 2 is going to be 1.25 milliamps. And resistor 3, or resistor 1 there, it's going to be 1.25 milliamps. So we can take that information and just go ahead and write it right down here. 1.25 milliamps, 1.25 milliamps, and 1.25 milliamps. Well, we almost have half of our table done. Isn't that exciting? Now, we need to find our voltage. Well, how do we find our voltage? Well, we know the current, we know the resistance. So what law? Let me think about it. Oh, that's right. Let's use Ohm's law to find our voltage. So we take 1.25 milliamps times resistance 1, which is 1K ohm, and that gives us 1.25 volts. And 1.25 milliamps times 1K ohm gives us 1.25 volts, and 1.25 milliamps times 2K ohms, because it's our value for R3, gives us 2.5 volts. So let's do our little gut check here. So let's take a look. We've got 1.25 volts, 1.25 volts across resistor 2, and 1.25 volts across resistor 3. And, whoops, how about 2.5 across resistor 3? And 1.25 plus 1.25 gives us 2.5 plus 2.5, which gives us 5 volts. So we have not violated Kirchhoff's voltage law in any way or shape. So now, when we go to find the power dissipated overall, well, that is equal to the voltage times the current. And so we take 5 volts times 1.25 milliamps, and that gives us 6.25 milliwatts. And for this one, we've got 1.25 volts times 1.25 milliamps, which gives us 1.565 milliwatts. And once again, 1.25 volts times 1.25 milliamps gives us 1.565 milliwatts, and 1.25, whoops, yeah, that worked. Well, 2.5 volts, I keep thinking that's, times 1.25 milliamps gives us 3.125 milliwatts. Well, 1.5625 plus 1.5625 milliwatts comes up to 3.125, plus 3.125 gives us 6.25 milliwatts. So, yay! It worked again. So let's do one more sample. Okay, here we go. Now, we have trouble. We have trouble because I look at this one and I see that that voltage source does not have a value. Well, I guess we must be done. Oh, wait a minute here. I see that I have a voltmeter across resistor number 1. So, I can take this information, I can say, hey, I got 10 volts there. So I can write this down, 10 volts. Woohoo! That's exciting. Okay, so what can I do with that? Well, oh, that's right, we can apply Ohm's law. And we can say, all right, I know the resistance value of R1. So I can say 10 volts divided by 1 k ohm gives me 10 milliamps. Oh, wonderful! Because we now know that we have 10 milliamps of current going through that resistor. That means how much is the current here? Oh my golly, it's 10 milliamps, and it's going to be 10 milliamps here, and that means our total current is going to be 10 milliamps. Oh, that was awesome. So let's go ahead and write that down. All right, 10 milliamps and 10 milliamps. Oh, cool. Can I find my total resistance? Certainly, I certainly can. So let's go ahead and do that. So our total resistance is going to be equal to R1 plus R2 plus R3, which is 1 k ohm plus 2 k ohm plus 5 k ohms, which equals 8 k ohms. Oh, awesome. Write it down, 8 k ohms. We're doing good. Can I find the voltage across R2? Most definitely, because we can say, all right, 10 milliamps times 2 k ohms equals 20 volts. And we can say 10 milliamps times 5 k ohms equals 50 volts. Now, can I find the total voltage? I certainly can, because I can do Kirchhoff's voltage law. And if I take 10 plus 20 plus 50, so we got 10 and we have 20 volts here and 50 volts here, we know this has to add up to 80 volts. Well, let's check that. 80 volts divided by 8 k ohms gives us 10 milliamps. Looking good. So how do we find our total power? Well, 80 volts times 10 milliamps gives us 800 milliwatts. And 10 volts times 10 milliamps gives us 100 milliwatts. Because remember, watts the unit for power. That's right. So 20 volts times 10 milliamps gives us 200 milliwatts. And 50 volts times 10 milliamps gives us 500 milliwatts. And note, 500 plus 200 plus 100 adds up to 800 milliwatts. Yay! And that completes the part on series circuits. Don't forget to come back and talk about parallel.